Okay, so before we sort of continue with the class, right? So I'll say a few words about projects. So projects is not looking for something to be just super original or super complicated. As for example, this sort of the well-known Kaggle competitions. If you go in, you can usually find many on electricity or having to do with energy. So this one is a little bit small, but it's basically tries to get you to predict the load of a building. And you can take one of these competitions and do a project for that competition. And so this is perfectly fine as an example. The nice thing about doing this kind of project is the data is clean. So they have the data all lined up, the data is clean, you can just go in and use the data. The risk is that your result may or may not look good compared to other people's result in this competition, right? There's a lot of people submitting to this. There's a bar basically for what you do here. But this is one example. So you cannot think of anything that's one example to do. There's other similar examples, like if you want to predict, let's say, electricity market prices. There's a lot of public data on that. You can go on there and do a prediction there. Right, so that's sort of there's a big source of project is this kind of prediction problems. As you either predict the load or you predict the price, or you can do some longer term prediction and look at the temperature change, look at the past load, do some forecasting of, let's say, how would global warming impact electricity load. All of this, you can pretty easily find data. Right, so that's one source of potential projects. Another source of potential projects is go a little bit beyond prediction, a little bit beyond sort of just predicting what happened. You can look at, for example, if you learn this model, how will you control the model? How will you control the buildings? How will you, if you say, I can predict the electricity price and I have a storage, how would I operate the storage? Things like this, right? So going beyond of predicting what is going to happen and look at some actions that you might take. So that's a more involved projects. Right? So projects like this where you predict building energy consumption, there is no action you have to do. You're simply making a prediction. Now, if you say, given this prediction, I want to do something better, then that's a control problem. That's right. So you have to take some action given your prediction. That's a harder problem, but so if you have sort of larger team, that's a problem you can think about. But more interesting than just taking data and predicting what happens in the future. Okay, but now doing this kind of predictions as a project is perfectly fine, perfectly fine project. Any questions about this? Okay, so if you haven't thought about projects, now is the time to start thinking about it. Try to think about projects, try to think about what you might want to do. Try to Google around and look at this kind of data source. So again, data is not difficult to find. There's data out there about anything you want to do. Anything you can think of, there's publicly available data out there. Right? So, but just to think about what topics that might be of interest to you. Questions? Yeah, go ahead. Sorry? Right, you can just email me. Yeah, feel free to email me. You don't need to find the data, right? If you have an idea, I can help you find the data. Right? So again, more of just thinking about what you want to do. Right? You may want to look at something that's of personal interest to you, or maybe just you just want to do this competition and see how you do compared to the other method that has been submitted. Yeah. Any other questions? Okay, right. So again, if you want to look at other sources of data, there may be some data cleaning involved. Right? So, but when I grade, I'll take that into account. Right? So if you decide to do a project where the data is clean, most submission for this one, for example, gets about 90% accurate, and your result is about 40% accurate. So that's not a great project. Right? So you should, if you do this for publicly available competitions, try not to come in at the bottom 30 percentile, this kind of thing, which is not trivial. Right? No, this kind of competition has money attached. This one is like $25,000 if you win. So there's people are motivated to do this kind of things. Right? So it's not trivial to say you're performing better than half the teams. Right? It's not trivial thing. Okay, but so just time to think about this kind of projects. Yeah, and today you have more and more of these sort of big money attached to this project. There's sort of more companies getting interested, right? For example, Microsoft and Google are very interested in grid. Of course, they're not power engineer companies. So one way to get involved and get a lot of people, talent, attract, is to run this kind of competition. So 50K is small money for them. It doesn't really, it's not a big cost, but then you attract like 100, 200 teams to do this kind of thing. So you have all of this kind of competition running. Right? So you can make a pretty good living by doing forecasting, actually, just doing this kind of things. Okay, so that's one to think about, but now something to start considering. Okay. So this for the project. So today we're going to pick up from regression again, and look at some. So last time was sort of purely invented data by me, right? So today we'll do a quick review on this and going to sort of more power system applications. You see where we use this kind of ideas in power system. Again, this is quite commonly used, right? So just to emphasize again, regression is really, really sort of central to data science, to this kind of when you work with data, right? So again, a lot of times for data, really what you have is you have some X and Y you can measure. Given some input, there's some box that will give you some output, right? So the goal is to find out what this box is. So one example that how this can be used is, let's think of this as a building. Okay, so let's say we're in this ECE building, right? We're in this building. This building can consume some, right? So this building consumes some power. So we can measure the power consumption of this building. We can very easily do this. What do you think drives building consumption here? What do you think sort of the factor? So this building does not consume the same amount of power every hour of every day. What do you think changes? The amount of power is consumed by this building. Or for other buildings, what determines how much power a building consumes? Think of some factors that might matter. Weather, right? Outside temperature, right? So outside temperature really matters, right? So here you can think of X. This is one. Why did I just say power? The power consumption. So outside temperature is a factor, right? So for this building, for example, it's trying to keep this internal temperature at relatively stable, right? So if outside temperature changes, you may have to cool or heat the building more or less, right? So outside temperature has a big impact on power consumption. There's one other thing that has an impact on consumption. So there's weather, there's one more thing that impacts building. What changes in a building like this? Right, so another thing that impacts is occupancy. How many people are in the building? Right, so depending on how many classes are going on, this actually changes quite a bit. Okay, so you have outside temperature, you have occupancy. These are sort of external things you don't, you don't really control this two, but this gives you power consumption, right? So you can now ask a prediction problem to say, given occupancy and outside temperature, can I predict how much power this building is going to consume? So this is a very common question we ask. We do this, for example, trying to predict for tomorrow how much power is going to consume. We do planning, years ahead, inputting some temperature and occupancy to how this power changes, right? Okay. So for building like this, it is true that there is a physics-based relationship between these two, right? So buildings are, what determines temperature or heating and cooling buildings, basically airflow. The way you heat and cool a building is you pump air through the building. You try to keep the temperature constant in the building. So the actual physics relationship between the input and the output, there is one. It is a heat equation that is a partial differential equation for this type of building with hundreds of variables. Okay, so there's almost no hope you ever find that. So what this kind of data, what data helps you to do is to say, I don't need to come up with that on your own. I don't need to fit that equation. What you can do is, this is extremely easy to measure. This is extremely easy to measure. This is for a couple dollars to measure. Occupancy is slightly more difficult, but still measurable. It's not all that hard. For this type of building, the way you do it is you basically look at Wi-Fi. Like how many devices on Wi-Fi, it gives you a pretty good idea of occupancy in the building. Okay, so you can measure all of these. This is very low cost. Then what you do is you basically run a regression between X and Y. You say, I know there's some input, some output. I don't know what the actual box is. I don't know what the actual function is. The way you do it is you run this regression, trying to relate X to Y. Okay, and the way you do it is basically you look at your data and say, how well can I predict some of the, how well can I predict from X to Y? And let me optimize my model that relates X to Y. Okay, so the the physics-based approach is, you pay somebody, you will construct the actual heat flow equation for the building. That cannot be done for most buildings. So now you can just take data and fit a model between the two. So you have many choices to fit this model, right? You can do a linear regression. You can think of Y depends linearly on X. That's what we've been doing. This is you can have nonlinear regression. You can think of maybe Y does not depend linearly, but depends non-linearly on X, right? So maybe depend non-linear, if the outside temperature is very cold or very hot, there may be a non-linear dependence on this. This is fine. You can, look for the neural network. You can fit many, many, many other things. And then think of what Y is, right? So a lot of this class is basically looking at this kind of approach. To say that you have some input, you have some output. You believe there is a relationship. That's typically easy. You can sort of easily tell there is a relationship. You don't know what it is. Okay, you don't want to spend effort, or it's very difficult to figure out what the true relationship is. So you take the data, you try to fit this. That's all what regressions say, and this is a very useful way to think about the problem. Okay, again, today is sensors are cheap. What enables this is sensors are cheap. Okay, so measuring power in a building 20 years ago was fairly difficult. Measuring power in this building now, the sensors, so you take a sensor, you don't even need to open the wire. It's a clip-on sensor. You can measure power. Okay, so all the sensors are getting very cheap, right? So all this you can do as you want to find this. Okay, so linear regression is just one way to do this. So in this sense, a linear regression and neural network is not really philosophically different. Okay, just a more complicated model that we want to fit. Okay, all right. So when we say we fit a model, basically there needs to be some mathematical parameters we can tune to make the fit better. Right? So that's where sort of different this kind of model comes in. Okay? Right? So linear regression, basically, if you believe this relationship is a line, right? You can plot this, and if you believe this is a line, basically the fit tells you that. So let's say you believe this, y is x equal to b, you observe some data. And then you basically tune this. You tune these parameters. Okay? You just tune these parameters until you get a good fit. Right? So that's the idea of the fit. Okay. So the idea of residues is basically to do a fitting, to do a regression or to do this kind of data fitting. You need some parameters you can tune, right? So for this line is the intercept and the slope. I can change these to adjust how I fit. You need two things. One is a set of parameters you can tune, you can change. Second is a way to measure how good the fit is. Right? So there's basically two things you need. You need something to tell you is a fit good or bad, and then a way to, because based on the fit is good or bad, tells you how you change your parameters. Right? That's the whole idea. As you need, if I give you A and B, let's say I give you some A and B, you need to tell me this good A and B good or bad. Then based on this error, whether it's good or bad, you need to be able to adjust your A. Right. So this is the whole idea of regression. Any question about that? So you're tweaking the model to get the output to fit the data. Right. So fitting the data, there's some cost associated with fitting the data. Okay. So there's many types of cost we can use. Okay, so again, we cover, so we always start off as we look at linear regression with least squares. So linear regression means that we believe that y, or y is equal to, or let's say that y hat, our prediction. Okay, so this is our parameters. So we're gonna change this weight matrix W. Right? So that we can change this matrix W. Every W we pick give you some relationship between x, right? Between x and y, between input and output. Okay, so we can pick some W, they'll give you some x between x and y. And we pick the error we look at as the least square. This is y minus, this is data. So y and x are data. And your goal is basically saying that look at all W's where this norm is minimized. Okay, so W is the parameters you can tune. The way you judge whether W is good or bad is you look at this distance. You look at this some cost or this norm. You say W is good if this is small. In particular, you want to find the W that minimizes. If in particular, you want to find the W that minimizes this norm. Okay, so we want all right. So any questions about this? Okay, so this is, once you get to this point, this is just optimization problem. And in principle, your computer can solve it. Okay, right. So if you, even when you look at much more complicated models, let's say this is a neural network, you do the same thing. Neural network is just something with a bunch of parameters. You're still tuning those parameters, trying to minimize this least square. And you're looking for the parameter that gives you the smallest error possible. Okay, give you the smallest possible error, right? Right. So We start with this is because this is particularly easy. The reason is you can actually analytically find W that gives you the smallest error. This is particularly easy because you know actually based on X and Y, you know exactly what the thing is. You can find what W is. All right, so you basically you have X and Y, you want to minimize this W, and just turns out this is there you can have a closed form solution, right? So again, to recall is you're minimizing over W, right? So again, you're always minimizing over the prime term. You're not touching the data. The data is given to you. Your job is once the data is given to you, optimize over your model relating X and Y, right? Your model relating X, Y. Okay, so again, the reason this can be solved easily is suppose yi is a scalar. So then you're basically minimizing y squared. Then this becomes sort of something very easy to minimize over. Okay, so basically it turns out this equation always works. Is if you stack your data as y, x, then you always get this equation. You always get this as your solution. This is a W that will minimize at least squared. The reason you get this is you take a derivative, set it to 0, you solve that, then you get this. This is why you see this inverse. This coming from taking a derivative, solving that linear equation, this 0 shows up. Okay. So this is nothing very difficult about this. Okay. Okay. So this just says that the best fit, of course, depending on the data you give it, this is the best fit. This is the best fit. Note that this fit, this minimizes the least square error. But even for this optimal W, the error is not 0. Okay, so one thing to remember is this minimize the error. It doesn't mean the error is 0. Right? So the error is not 0. This is not. Right? So this makes the error as small as possible. That doesn't mean you can make the error 0. It doesn't mean you can perfectly explain the data. Right? There's some non-zero. Right? So any questions up to this point? Okay, so this is the whole point of least squares, right? I mean, this whole point of the linear regression is that you have this closed form formula, you can plug into this. This is a very simple form. Okay. So there's several reasons why this is not typically 0 and why this may be, still fairly big. Right? So one reason is that maybe the data is not linear. So what this restricts you to say is you are only taking linear functions of x, right? So what you're searching for the best linear fit. Right? So this W is the best linear fit. It is not, right? So you're restricting your search over all linear function of x. That explains why. So if the true ratio is nonlinear, this will not be 0, maybe very large. If you have some noises in the data, for example, this will not be 0. Okay. So there's no guarantee. Typically, you cannot just look at the value of this fit and judge whether it's good or bad. Okay, because it's typically never 0. So it's not clear if you just look at this whether it's good or bad. Okay, so just some non-zero value. You're guaranteed that W is the best linear fit, right? But it doesn't really. So it's not always true that this error very small, or there's no better fit. Right? And another reason why least square is not enough is very sensitive to outlier. Right? So you may have a data that's explained by a line here. You have one point that's an outlier. Then you suddenly this skews this entire thing. Right? It's very sensitive to even a single point being outlier. Okay. Why is this? Why is it so sensitive to say, a few or one point? That's extreme outlier. Right, so we go back to the building example, right? This happens as, let's say, you have some error in your sensors. There's one data point that because of error, you measure the temperature to be abnormally high or abnormally low. That single point will actually pretty much destroy your fit. It's extremely sensitive to this kind of error. So what's the mathematical reason behind it? Right, so the reason behind this very sensitive error is comes from the square. The distance is measured in terms of the different square. So right, so if you square some number, if the number is small, you square it, it's closer to 0. So you have a lot of small errors. When you square them, add it up, it will be dominated by a huge number square. Okay, so when you square a bunch of things, one particular thing being much larger than others tend to dominate. Okay, so you have, so here's your least square is, so you're basically looking at summation of yi minus, so you're summing this thing square. One term can dominate all others. A big term can dominate all others. So the square is, so something squared is very sensitive. Okay, very sensitive big values. Right? So here you may have many points. Each one of them may have a, say, distance of 1. So you square that, you may have 100 points here. Each one of them have a distance of 1. You add all that, has a total area of 100. You have one point that has a distance of 10. You square that, that's 100. Right? So this one thing will dominate all of this, right? So there's just an inherent difficulty with this square being there, this two norm being. It's very sensitive outliers. Okay, so that happens. So the way we deal with this is often just start using different norms. Okay, so the way to deal with this, and this is actually very important, you basically change this 2. If you say, if this is a 2, you're very sensitive to this outlier. What can you do? As you don't have to square this number. Maybe you can look at the sum of absolute value. Maybe you can look at other things. So another way to deal with this, so the way to normally to deal with this being very sensitive to outlier is you just change the way how you measure distance. Okay? So the way we change it is you can think we introduce something called the Q norm of a vector. Okay, so Q norm of a vector is written like this. This is some vector U. This notation means the norm depending on Q. So what does this do? This is okay. So this has just this sort of funny looking equation. This, so you can plug any number Q. So this, of course, this needs to be positive, and typically this is bigger than 1 for it to be a norm. But you plug in a number Q, you can sort of find this kind of numbers. Okay. So what does this, So for example, this is a 2 norm as this is just a standard 2 norm. This is the Euclidean, right? This is the Euclidean distance of U. This is the length of U, defined this way. You can plug in 1 there. You can say this is 1. Then this is just the summation of the absolute values. So 1 norm is just summation of the absolute values. 2 norm is you square this thing, you take the square root. So what this does is basically the larger the Q, the more sensitive it is to the largest value in this vector. Okay, so this is a way to assigning weights to the largest maximum components. Okay, so the larger the Q, basically this Q if Q is large, this amplifies the largest component. So the larger the Q is, the more it amplifies the importance of a large component. Right? So the smaller the Q is, the more it treats everybody equally, basically. Try to treat every component equally. The larger the Q, try to exaggerate the importance of the weight. Okay? And you can have extremes actually for this. Right? So for example, one extreme you can ask is, what happens if I take Q to infinity? Anybody can see? What happens if I take Q to be very, very large? Right, so there's very well sort of no norm. This is called infinity norm. That makes you take Q extremely large. Not zero. Right? So if you take Q extremely large, what does it do? Which component does it pick up? The largest one, right? So take Q very large, it picks up the largest component. This is the max over I ui. Right? So you're basically looking at, right? So if Q is very, very large, this whole thing is dominated by the largest component, right? The other smallest ones doesn't matter. The largest one dominates. When you take a Q's root of it, you basically destroy, you kill all the other smaller ones, only the largest ones survive. So that's what's called infinity norm. That's basically how you take a max. You can think of this, given the vector of numbers, how do you define max? You can actually define max this way. I should just think of you looking at this kind of norm. Okay? So that's define max. You can look at the 0 norm. Basically, this is when Q goes very, very small. Okay? So when Q goes very, very small, what happens is this is just a number of non-zero components. Okay? So anything that is not 0, if put to 0's power to it, becomes a 1, basically. Right? So anything that's not 0 is a 1. So at the end of the day, just summing up, looking at how many components are non-zero. Okay, so this is the way that basically most of the time when we think about different metrics or different way to measure error, you're basically picking one of these norms, or you're picking a combination of these norms. You think, do I want something to be, do I want to emphasize the largest error, or do I care about just how many components are non-zero, this kind of thing. Okay? So these are different norms you pick up. You pick up different norms. All right, so these do matter. These do show up in power system, especially. This shows up, for example, when you look at the max of a vector. Again, typically because the power system is, the cost associated with consuming demand for large consumers is often associated with the largest hour demand you have. So often in power system sort of pricing and utility bills, you basically build on your infinity norm. not the two norms, for example. Okay, so you look at infinity norms. Other places you may try to count number non-zero element. So all these norms matter. And basically they're a way to sort of often deal with outliers. They often deal with outliers. Because in this picture, you can outlier is easy to spot. You can plot it. You can say, okay, that point is outlier. You can ignore the point and rerun this. When your data, when you have a lot of data, and especially if they're not two-dimensional, it's not trivial to detect outliers. Actually, outlier detection by itself is not a trivial question. Like, how do you even define a point being outlier, right? It's not easy. So normally the way you do it is you go from a, say, Q norm to something else. So there's different Q norms. You pick different values for Q. And the interesting you can draw is basically, you can draw when this norm is equals to 1. So this is called a unit ball. So basically Q equals to 2. The unit length vectors of unit length vectors for the two norm is just a circle. This is saying u1 plus u2 equals to 1. u1 squared plus u2 squared equals to 1. This gives you a circle. One norm gives you this diamond shape. Right? So, larger norms basically become a square. This is geometrically how we think about points. Okay, so for the two norm, when you assign distance, this distance and this distance, for example, is equally distant from the origin. If Q is larger, you're basically blowing this up. This point and this point are all equally distant. Q is 1, right? So this point, which is on the circle, is further away from the origin. So basically think this is different ways of thinking about how far a point is, okay? how large the point is. And in practice, often is pick a Q that fits a problem best. Okay, so the often question comes down to, based on the context, you have to pick a Q. Sometimes you want a two norm, sometimes you want a one norm, sometimes you want something else. Okay, something else, right? So in the next homework, we'll have questions exploring what happens if you change this Q. Right? So if you fit the data, you pick two norm, what happens to the fit? You pick one norm, what happens to the fit? Okay. Yeah, we'll look at this kind of questions. Okay. Any questions so far for this? Okay, so I'll say one word of caution is, in practice, when most times stay within Q equals to 2, Q equals to 1, or Q equals to infinity. The three norms we use by far the most common is the one norm, the two norm, and the infinite norm. There's a reason for that, is when Q equals less than 1, it's actually very hard to optimize the problem. It's very hard to find the best fit. So the reason is because the problem is non-convex. But anyways, Q less than 1 is very hard to work with. Okay? So we typically don't look at that case. Anytime Q becomes larger than 2, it's essentially the infinity norm anyways. This is very similar to what the infinity norm ball looks like. So in practice, we basically look at combinations of, in practice, plus 1, 2, or infinity. And so we look at all these different norms. And so it's, either one of these or a combination of these and different things. And again, your computer will solve this for you. So we'll have no closed form formula for one norm or infinity norm, but there's still one line code how to do it for you. And so we're not going to worry too much about how you optimize this W. Right? We're not going to think about, so this is W transpose Xi. We're not going to worry too much about how exactly you go and solve this minimization problem. Suffice to know that for Q equals 1, 2, or infinity, there's a one-line code that will do it for you. So internally it's doing something, but you're guaranteed to find this W. What we're going to do is we're going to look at how do you interpret this result, right? So for different W's, how do you interpret what they mean? So one homework will ask you, for different hue, try out giving different data, try them out and see uh, what the conclusion you can draw. And one thing with all the homework questions, they're designed to make you draw a conclusion. They're not designed to trick you, right? They're not tricky questions. They're designed to make you, see something. Okay, so when you do the question, it should not be, blindly typing something and something comes out, right? So they're not, again, they're all supposed to be easy. It doesn't take that long to program them. But each homework question is really trying to make you see a phenomenon that you're supposed to see. Okay, so that's really what they're trying to do. And again, your code, well, for this kind of thing, will all come out to be a few lines at most. Most of your code will be plotting. The actual code that computes W is 1 or 2 lines. The rest is how do you plot all the things, right? So there's not trying to be tricky there. And then what your homework trying to get you to do is again to look at what happens if you combine different norms. What happens if you combine, for example, 2 norms with 1 norm? What happens to the set? Okay, so we'll look at all these different settings and trying to for you to gain some intuition. But if you get real data, how do you do this thing? So this is, for example, if take Q to be 2 here, this called rich regression. What this does is to say that I want to fit the data well, still with the 2 norm, but I do not want my coefficient W here to be very large. Okay, so I want to fit the data, but I don't want very large coefficients. Right? Because when large coefficients happen, you're very sensitive to noise. Okay, so this says I want to control my model not to be very large, but I still want a good fit to the data. So these are ridge regressions. You can take a look at these approaches. And the reason, so one thing you see in the homework is the following, that often your data looks something like this. Okay, so I'm going to draw using different colors. So you can think of basically, you can ask a question as I have a bunch of red dots. So your homework will give something more, more numbers, but the picture looks something like this. So if you have some red and blue dots, you may want some line that separate between red and blue dots. This is a very common problem that comes up. I want to separate, one side of the line is all red, one side of the line is all blue. Okay? I may want this kind of thing. What you can have is, right, so what could happen if you don't have this regularization term? What could happen is you have some very complicated looking shapes that can actually separate red and blue. There's some extremely complicated shapes that can actually separate the two. Not often is not very useful, right? You can have sort of overfitting in this kind of context. And what this regularization was to prevent overfitting. So what doesn't, so let me draw this better as I say that, I draw this with less number dots. So let's say you have some dots like this, right? Okay, so now you can ask, okay, what curve separate out red and blue? Yes, is there some curve that where blue is on one side, red is on the other side? Okay. The line doesn't work, but there's many other curves that does work. So what you want is you want to avoid some curve that looks, very weird. Okay. So this is one curve, for example, that separates blue and red. This is a perfectly fine curve. This minimizes error. Point are on 2 sides. This is obviously, so this is called overfitting. As your model is overkill, sort of too, it does a job, it gives you small error, but it's too complicated. And what this regularization typically does is corrects for overfitting. It sort of tries to make sure that whatever your model is trying to use is not too large. The model is not overly complicated in here. Okay. And the regularization, again, there's sort of many theory behind this. There's a lot of theory behind this kind of, there's a lot of theory behind, what happens when QX2, what happens QX1, and so on. This, especially this lasso, when you have a two norm here regularized by one norm, this was a huge advance in signal processing. This is huge advance in signal processing to figure out the sort of theory behind this. We are not going to worry too hard about this. For us, we're going to just try a bunch of things and see what happens. Okay, but again, do not. You may hear a lot of today's technique, right, on deep neural networks and things like that. A lot of times, still, this kind of simple regression with regularization works. Like many settings, this thing works. And all you need to do is basically try different norms, try different combinations, and will work fine. Okay? So this is one example of the fitting, right? So what this is the up to 2015. This is the miles of vehicle traveled in US per month. Okay, so what it does is here is time. Here is sort of how many miles people drive in total. Okay, so different months in the US, you compute how many miles people drives, and you can have this kind of data. Okay, right? So you can ask question, okay, can I fit on this data? Right? Can I predict? Can I understand what drives this? Okay, so for example, one attempt of fitting you can do is you can say, well, so if you look at the data, right, one is there is a clear seasonality. People drive more in the summer, less in the winter, more in the summer, less in the winter. There's clear seasonality. So one thing that the X you can take, right? So in this case, X is seasonality means that X has to do with month, which month, okay, month of the year. Okay, so you're coding January, February, and so on, in month of the year, gets coded here. You can have a trend. Okay, so maybe you see, we started driving more, right? So over 15 years, we start driving slightly more. You can access the month of the year. Trend is basically year, which year you're in. This is the trend. Okay, you say from these two, can I fit relationship Y, which is just the miles driven, or miles traveled. Okay, so miles traveled per month, right? So we ask, okay, from this X, can I predict what? Turns out you can. What you need to do is basically you just use ridge regression. So this means you regularize your least squares with a two norm on the weights. You can actually get a pretty good fit. This is a simple regression you can do here. And even for these two, even if you use a neural network, it's not going to do much better than this. One is not going to do better than this. And the value of fitting things this way is if you want to explain this to, for example, policymakers with linear regression, you can read out the weights that depend on the month and the weights that depend on the trend. This is a very easy thing you can explain to people. Whereas if you use a more complicated model, one, it doesn't do better. Two, it's hard to explain. Okay, so for this kind of fitting, this is often you just end up using this kind of thing. This works. This works pretty well for a lot of things. And one project you can do, related to this is, for example, you can say, okay, now let's say I have electric vehicles, and I take a fraction of miles traveled by electric vehicles. Let me project that forward in time with months of year and trend, for example. Let me see, how much emission is saved if I replace 10% vehicle by electric vehicles. And let me see how much emission is saved if they're driven in the winter versus summer. Let's look at electricity cost in winter and summer of charging EVs because electricity also price also depends on seasonality. It is cheaper typically for some seasons, more expensive for other seasons. Right? You can, for this kind of planning, you can ask, okay, this is the miles kilometer of vehicles, this is carbon emission saving, this is the cost of charging them, and so on. So that's a good project you can think about. Right, so this is what I'm thinking about projects. For this type of interest, you can find this kind of data. All this data is out there somewhere. So interest in EVs, we can find data on miles traveled and EV adoption, this kind of thing. So we can find out. You can do this kind of calculation. Yeah. And we do this in policy. If you work with a city, with Seattle, for example, you compute this a lot. You do this a lot. You take data, you look at what are the plausible explanations. You have a fit, hopefully it's pretty well. The good thing is you can explain to the mayor or your boss what all the things mean. Whereas if you use a very fancy method, you may not be able to explain to people what it means. Right? So a lot of choosing model, one is how good does it fit? Second is, does it enable you to do the other things that you want to do in this case? Okay. All right, so from after this, we'll look at actually one thing that's very specific to power system that uses both regression and regularization. So power system is, so this is a problem called state estimation. Okay, so we'll take a break in a little bit and do sort of review of power flow. But the state estimation for power system is following. The interesting thing is that what drives power flow across the transmission line? Anybody know? What drives current flow in a circuit? What causes current to flow in a circuit? So in AC circuits, especially in power systems, it's not the voltage magnitude that drives current flow. Everything operates pretty much at the same voltage magnitude in the transmission network. What drives power flow is actually the phase difference between the voltage. So the angle difference in the voltage. So remember we have AC signal. So everything is offset. There's a phase offset. So that phase difference actually drives power flow, right? Between different across the transmission line. So it is a voltage, but it is actually the angle part of the voltage that drives, not the magnitude of the voltage. And the problem in power system is it easy to measure the phase offset of a sinusoid? Why is it hard to measure the phase offset of a sinusoid? So for example, if I take a measurement in this building, and I say I take a measurement at a building across campus, let's say in the main library, right? So let's say I take a oscilloscope here, I look at the sinusoid. I go to the library, I take oscilloscope, I put in the wall, measure sinusoid. Can you tell me the phase difference between these two sinusoids? No, right? Because you need a common clock to tell the difference between sinusoid. All sinusoid on the oscilloscope look exactly the same to you, 60 hertz. The way you tell the phase difference is you need a common clock. In power system, typically we don't have a common clock. I don't know where your clock is, let's say in another building compared to this building. And the clock accuracy we need is actually quite accurate. So your cell phone clock is not that accurate. But remember, this is 60 hertz. The accuracy needs to be much smaller than 1/60 seconds. So in power system, the problem is that what drives power flow is the angle difference across a line. We cannot measure angle difference because I don't have a common clock. So I don't know the reference of the two sinusoids. So state estimation is basically from other measurements, you have to figure out what the angles are without directly measuring them. This is something that's run every minute of every day everywhere in the world. So right now, some computer in BPA is running this problem, solving this problem right now. Okay, so solving every minute. So let's take a 5-minute break. Then we'll do some more reviews and look at how data is used to solve this problem. So here, let's say we have some relationship between x and z. So this is called, let's say z is equal to h of x. Okay, so this is called a forward function, right? So this given state, you can very easily find what the output is. Okay, given state, you can find the output. Okay, so let's look at an example here. So let's still look at this example. Okay, so let's say that you have theta 1, theta 2, theta 3. So here, let's say you have P1, P2, P3, P2, 3. Okay, so here we're going to look at this example as your x, the theta 1, theta 2, theta 3. Z is P1, P2, P3. Right, so this is just some example. Right, so in this example, your state is in the angles. The output, Z, is the power flow. And we can write down the equation linking between x to z. Right, so I'm going to write down this equation. So let's say the line parameters are B12. And say that P1 is equal to B12, theta 1 minus theta 2, plus B13, theta 1 minus theta 3. Any question was where this equation comes from? Right, so P1 is the power coming out of node 1. Right, it has two parts, power flowing from 1 to 2, power flowing from 1 to 3. So B12 is a line parameter, theta 1 minus theta 2 give you the power flow along 1 to 2, B13, this gives you a power flow along 1 to 3. Well, B13, this is the parameter on the line, so how inductive the line is. Right, so different lines, right, so it's proportional to the angle difference. But normally, right, so think of normally when you have current flow, it depends on the resistance of the line. So here it just depends on this, not the resistance, but some physical characteristic of the line. Okay, good. Any other questions? Okay, so you have this equation, right? So P2, this is B12 theta 1 minus theta 2, theta 2 minus theta 1, B23, theta 2 minus theta 3. I'm going to write all this out. P3 equals to okay, so these are the node injections. And we're going to look at P23. Okay, so this says from the angles, if you give me the angles, I can compute all of these, right? I can compute all of these easily by using this type of equations. So you can summarize this. You can put this into a matrix, right? So you can have V basically is P1, P2, P3, P23 equals to, so you can write this as a matrix, B12 minus B12. Right, so I'm going to write basically collect all these set of equations into a matrix form, into a matrix equation. So there's nothing too deep going on. This is just writing this out as a matrix equation. Okay, so this is our equation we're going to look at, right? So x are the thetas. This h is just this matrix thing. This matrix, you multiply this x by this h matrix, you get the output. Okay, right? So this is again, this is the forward equation, right? So given x, it's very easy to find z. right? Okay. Any questions for this? Yeah, go ahead. Yeah. Oh, let's say that we did not install a sensor there. So this is all the sensors we installed. Right. We don't have to measure everything. We have to measure a subset of it. Right. So okay, good. Right. So let's say we just happen to measure all these things. We can measure. Okay. So this direction is easy. Given state, compute those is easy. We're we're not gonna look at this. The problem we're interested in is the reverse direction. So we're not gonna say that given z, find x. Okay. So given x find z is easy. You simply put x through the function h, you get z. Now the question is, given z, can you find x? So is this a well-posed question? Right? So does this question make sense for this problem? Let's say if I want to measure P1, P2, P3, P2, 3, can I find all the angles? Yeah, this is a well-posed question. So to look at it, think about it, right? So if I give you z and ask you to find x, it's basically asking you to solve a linear system equation. How many equations do you have? How many variables do you have? Can you solve that system? If you have more equations than variables, what happens? There's no solution. So this question is actually not well posed. So a more better posed question is, this is not good as a question. It's not doable. Because you give me four numbers, you give me four equations, I have three of those. I can't solve the equation. Okay, so the actual question you ask is given a noisy version. Because whenever you measure, every measurement device has noise. So you're not measuring the true Z, you're measuring a noisy version of Z. Given noisy Z, find X that best explains Z. Okay, so that's the question that what state estimation and all this data fitting asks you. It's not given you measure the output, find the input. Typically, you cannot do that. There's more alpha than you, right? So there's more, you can install a lot more sensors than typically when you have the state. So the reason you see a lot of sensors is every sensor has noise. So given some noisy version of the measurements, find me the state that best fit this noisy Z you have measured. And so what we're going to ask, again, we're going to ask for a Z that gives you the least square fit, not that the Z that solves this type of, all these equations simultaneously. We're not going to ask, so this is not an equation solving problem. This now become a data fitting problem. Okay, saying that given some Z with noise, this measure doesn't change. Find things here that are most likely got you that. Okay, so that's the question we're gonna ask. Okay, so we're not doing equation solving, right? There's a tendency for this kind of problem to go and try to solve this equation. You cannot do that because you have more equations than variables. And you can't solve the equation. So that's why we're gonna think of this from a data fitting perspective, right? What is the most likely, what is the best state that you can get that explains your output? Any questions on that? Okay, so we're gonna see how we do this. Right, so we're gonna start with the linear fitting. So for this, it's basically think of that. So we're gonna skip this. We're gonna say that assume power flow is linear. Okay, so all of this is again repeating that if you have two lines, P12 going this way, theta 1 minus theta 2. Okay, so the line has a parameter b. This depends on theta 1 minus theta 2. So P21 equals to minus P12. This is b minus b theta 1 minus theta 2, or b theta 2 minus theta 1. Right, so this is called, there's a name for this, it's called the DCOPS. This is called the DC power flow model. Basically just says everything's linear. We're going to assume things are linear. We're not going to worry about sine and cosine sections because that's too hard to deal with. So just take the linearized approach. This is actually what's done in practice. So the actual power flow equations is a lot more complicated than this. We don't use that is because we cannot actually solve that regression problem in practice. So we just do linear ones because we can solve it. We can solve this. Okay? So this is power flow along one line. Then of course you can have right. So you can have, let's say this is I, this is K1, K2, K3. Then the total power injection at bus I is given by this equation, right? Just summing up the power that flows to each of the branches. And this is again a very sort of quick calculation or definition actually is that you have a node, your total power flows along these branches, where for each branch is driven by the angle difference, by this angle difference. All right, and then from these equations, you can always write down what we can write down P equals to P theta, and thus you build the network. And so there is a systematic way of doing this. For this class and for all the homework you have, the system is small enough, you just eyeball this P. So what you do, you're just going to eyeball this, right? So you say, for each bus, you write down this thing, and you just write down what the linear equation is. So we're not going to talk about how to systematically construct this. Okay? But this is basically just a fairly straightforward way to write down this matrix B. Okay? So we can write down this matrix B. We have power. We also have line flow measurements, right? So we can not only sort of measure the total power injection, we can measure some, line flow injections along particular lines. You can write down flow also fairly easily. You can write down flow equals to I times theta. Again, for this class, matrices B and F constructed by inspection. So basically this is everything you see is small enough, you just look at it, you can write down this matrices, where it's not really worth the effort to write down the construction, right? So there's actually quite a bit of deep math behind the properties of BNF. If you do research in this area, we spend a lot of time thinking about this kind of matrices. But for now, they're just constructed by looking at the network. You just look at it, something comes out of the network. And then we're going to stack the measurement basically into a vector. So Z is some flows, some power measurement. Okay, so we don't need every measurement in the system, right? We can take a subset of the measurements and construct Z out of it. Okay, so we Not every line is monitored, the flow is monitored. Sometimes when you measure power injection, you may have a sensor error and things like that. So Z is just subset of this flow and power measurements you have. And what we have is we have Z equals to Hx, X is the angles. Okay, so X is theta. Okay, so this is our equation we have. Now given given X, we can very easily find Z. Now the question is, if we measure Z, can we find X? Okay. Questions about this structure? So again, the thing to remember is this can be this is just a subset, right? So normally Z is not, even if you have a large network, this is not a huge vector you measure. Okay, so you just measure enough of this. And the estimation is such that given ZH, find X. Okay. So this is not, again, equation solving because of noise. And noise is a real thing, actually. So in sometimes when we sort of do questions, we pretend there's no noise. In practice, whenever you measure, noise is not small. Again, in power systems, we're talking about powers in terms of like tens of megawatts, hundreds of megawatts. So in power systems, our measurements in power a lot of times, we don't measure below a megawatt. Okay, so a megawatt is not small, but often we're just not that sensitive to variations under a megawatt. Okay, so again, noise is a real thing. So there's always noise. So the actual model is the thing you measure comes from the physics plus noise. Okay? So because there's noise and we don't know what the noise is, we cannot directly solve the equation. Okay? Noise is unknown, right? You never know what the noise is. The reason it's called noise is you don't know what it is. You know, there is noise, but you don't know what it is. So, no, no. So we cannot solve this system. Okay? So we don't solve this system directly. What we do is we ask for a least square solution. Right? So you have noisy measurements. And the least square approach to this is we're going to ask the following question is, when we look at minimizing X such that this is minimized. Okay, so this is our least square solution we're going to look at. Right, so it's a very, very similar to linear regression. Except right now, your X is not the weight anymore, X is your state. Everything else is exactly the same. But DC power? Yeah, this comes right. So this H comes from DC power. Okay. Right? B theta 1 minus theta 2. Yeah. Do you mean active power? So in this lecture, in this class, we never talk about AC power, right? So we just have one, for this class, we just have one equation, which is this equation, right? We did not talk about AC power flow at all. So, sorry, which function was this? Mm-hmm. Yeah, yeah. Which one are we? I'm a bit confused. So all of our equation look like this, right? We don't have different equation. We only talk about one equation in this class, which is this equation. So how is connect to hx? So we construct h, right? So we did, this is your h, right? This h. So this is a matrix. This, are you saying this is not a matrix? This is a matrix. There is always a matrix, right? So we stack this up. This is a vector. The matrix multiplied by a vector gives you another vector. Right? This is how we think about it. Right? So the way we construct this matrix, we look through each of the terms. And you just say, right, so this is a bunch of equations. So how do we construct this matrix? Is you basically go read off all these coefficients one by one, and you construct the matrix. Right? So again, there's only one equation. Like this is the only equation you have. You can write it in a matrix format. And we're writing into a vector matrix notation. There's not two equations here. Yeah. Right. So this is one form, right? How do I get this matrix? I basically read off all these coefficients one by one. So do you understand how I got from here to here? So is your question like, how does this relate to this? Right? So okay, so the way you get from here to here is basically so these are linear equations, right? So it has to be some matrix multiplied by theta give you all this piece over there, right? So for theta 1, you look at first equation. Theta 1 has a b12 multiplied by it. Plus there's a b13 multiplied by this. So that's your first coefficient multiplied by theta 1. Theta 2 has a minus b12. So that's minus b12. Theta 3 has a minus b13. You write down minus b13 here. So you look at this, each of this equation, just write down the corresponding coefficient in this matrix. Yeah. Yeah, so there's no two equations. This are exactly the same thing. This is written in a matrix notation. Because it's easier to write in a matrix notation. Yeah. Okay. Any other questions about this? Yeah. Oh, so AC has a sine and cosine in power flow. Yeah. So AC is sine and cosine. So DC means linearized. In this class, we're not going to do AC. This is sort of a little bit out of scope for this class. Takes us a few weeks just to get through AC power flow. We're not going to. So AC power flow means the actual power flow equation. DC power flow means linearized. The reason it's called DC dates back to the 1930s. We don't need to go into it, but that's just a fancy word for linearized power flow. So this is phasors, right? This angles. Angles come from phasors. Yeah. The word DC. Okay, I see the confusion. Okay. DC has nothing to do with direct current. It is not direct current. A zero relationship with direct current. Okay, this is not direct current. This dates to 1930s. We'll not talk about the reason why it's called DC power flow. It is not direct current. It is not, yeah. It's just the reason it's called DC is 1930s. You don't have computers. So how do you study power flow? You actually build a circuit modeling your power system and use that physical circuit to simulate what happened in your power system. In that circuit, power gets replaced by current. And some guy in England has this weird idea of that should be called DC power flow. The name has stuck. It's not going to change. But when you see DC, read linear. Has to do with phasors, has nothing to do with direct current. There's no direct current business in this class. Yeah, DC stands for something circuit analyzer. I don't know what D exactly stands for, but it's not direct current. All this is phasor. The DC is not direct current. So phasors has angles, right? No. This DC is not direct current. This DC, again, dates back to 1930. Some guy decided to call linearized AC power flow DC power flow. So some guy 100 years ago decided when you linearize these equations, it should be called DC. I don't know why. Okay, so, but does not stand for direct current. If you want to think about it, think of this as somebody's name. We name it DC as a proper noun. Okay? It has as much to do with DC comics as direct current. It's a name. Yeah, we're not going to worry about why it's called direct current, DC. Okay, so angle is there. It's linearized where angle is the only thing that survives. It's linearized based on the angle. It's just not, yeah, it's just a word. Yeah. No, DC. So DC in this class always means linearized power flow. It always means DC anyway. DC power flow just means linearized power flow. No, DC power flow has angle. DC does not mean direct current. It's right. So this class we're talking about how do you measure the angle, right? You do this state estimation. You measure power, then you get the angle out of it. Right? The whole point of this class, this part of the class is to say it's hard to measure angle directly. It is easier to measure power. So we're going to measure power and we're going to find the angle by measuring power, right? Okay, so angles are difficult to measure, right? As we said. If you know the angles, you can find the power flow. Right? So the name DC just means everything's linear. Right? Replace DC with linear if you want. The reason we're doing this is because this is harder to measure, right? This is harder to measure. This is easier to measure. So we're going to measure the easier to measure things and figure out what the angles are. Okay, right? So angles is a physical quantity that exists. It's basically the angles of the sinusoid that you have. It's not easier to measure because we need a common reference that we don't typically have. So we're going to measure this thing and trying to figure out x. Okay? So this is what we're going to try to do. Okay. Good. Any other questions? So this happens a lot, where the actual state of something is not something you can directly measure. It's where you measure what you can measure and try to back out what the state is. For example, if you have a aircraft, right? So you fly an airplane, you have the speed and altitude of the airplane. You don't measure those two directly, actually. It's very hard to measure the speed of the airplane directly. So you measure something else. Then through calculations, you back out what the speed altitude of the airplane. Same thing with your car. So how does your car measure speed? Yeah, how does it measure, like, how does your car know it's 40 miles per hour? You have a speedometer, how does it know it's 40 miles per hour? But your speedometer doesn't do that, right? Your speedometer does not measure one point on the road, then compute 1,000 meters later and divide the time. Right, you have inertial system and you measure sort of revolution of your wheels. Then you back out how fast you're going on the road. So this is similar. It's sort of the actual state that you care about, you cannot get directly measurement to. So you measure something else, and these two calculations figure out the actual state of the system. Similar to how fast your car is going. Your car speed is not, your car looks like, oh, at this point to that point is a kilometer. And let me divide, right? It doesn't do that. The internally is measuring something else to figure out your speed. You can do that, but your car doesn't do that, right? Right? It doesn't do that, right? You're driving a car, you press the gas pedal, your speed changes. Your car is not measuring a small distance and looking at as computing the time, right? Your car is not doing that. No, I don't mean that. I mean the speedometer is the speed that shows up when you drive, right? There's, you do that through measuring other things, right? So here the power system, same thing. You care about these values. You can't measure it directly. So you measure something else and you try to get to this value, right? So that's the whole point. It's hard to measure them. So we're going to measure the year to measure. Right? And this is what happens for most systems that we have. Okay, good. Any other questions about this? So this is the important point of why we're doing this. So it's a good discussion to have this, why we're doing this measurement. Like you see this question a lot in the next homework. Your next homework is basically this question showing up in 5 different forms. So you have a question asked now. Otherwise, your next homework is not going to be very fun. Okay, so basically you have a network. Your goal is to construct this matrix. And you're going to do this thing using least squares, using one norm, using regularized fitting and all that. And I'm going to try to figure out what this is. Yeah, so it'll be similar to the last homework, right? So I'll provide some examples to say, this is what you do, you write this, it's a fit, nothing about following ABC. It'll be very similar to that question. Yeah. So the notebook will be basically similar to last homework you have. As I will give you some examples, get you started. And then questions will be asked after that, right? So the homework is not just be like question 1, question 2, question 3. There will be some examples to run you through it. A textbook for this? Not easily, no. There's power system books that does this, but you have to make it through a lot of background material to get to this. So mostly is sort of do the homework questions, try to get to this. So the homework will have examples. Then we'll ask you to expand on this example. But it's good for here at least to know why we're doing this kind of thing. Otherwise, it'll be extremely confused on what it's all about. Okay, right. So the reason why is again, so mathematically you want is given the get x. Physically is just because this x, this angles are hard to measure directly. And again, this is with most systems. For most systems, the things you care about are typically not things you directly can go measure. So you need to get this some other way. And so mathematically, this comes down to a least square problem, right? So the least square problem comes out is because, again, you know what this z is. This you know, this is your measurement. Because of noise, this thing may not necessarily, there may not be x that makes this distance 0. But you want to find the x that minimizes this distance. Right? You want to find the x that minimizes this distance. Okay. So this is exactly like linear regression with different names. Linear regression, X and Y means other, W means other things. Here, everything the same except you have different notation. It just things are named differently. And so least square is you're asking for the best X. So we want to find the X. This is called best explains the data. Okay, so here Z is no, or Z and H are no. Okay, so you know Z, you know H. Z is your measurement. H comes from the system you construct. Yeah, X is the way. You gotta think of X as the way here, which is the phasor. Yeah, which is the phasor. You try to find the phasor that minimizes this distance. You minimize. Right. You can introduce regularization, right? So, for example, we haven't looked at outliers yet, but here are outliers. You may want to say that the phase in my system cannot be very large, right? The angle difference is not huge. So there may be something you may want to regularize X. But before regularization, the most basic form is that I just want the phasors that best explains the alpha, that minimizes error. Oh, in practice, you solve this. This is exactly solving practice. As you measure the power, you ask, okay, what is the phasor that will produce this set of power measurements? The way you do that is solving this. You literally solve this equation. Yeah, right, right, yes, yes, yeah, yes, yes. In power systems, the phase angle difference typically across a line is very small. It's a few degrees at most. Right? So if you see an angle difference that's 30 degrees, either you have a data outlier or your system is about to blow up. Right? So both can happen, right? So you there's ways to tell which one is true. But when you add regularizer, yes, it's sort of reduce outlier, things like that. Good. Any other questions with this most basic thing? Maybe solving this. So in your homework, there will be one question is, I will draw a network, say construct, and say what Z is, what are the measurements. Your job will be to construct H and then solve this equation to figure out what the phasors are. And that's the most basic version of the homework question. I just do that. Right, so we'll get fancier, but I'm not going to assume that everybody can solve this. Right, this is just least squares. We can use the same formula we used before to solve this thing. Right, this is, or actually from this homework, we'll probably just call a Python command. We're not even going to use the call for formula. Just directly call command and solve this. Yeah, so before the first question, there'll always be examples leading you through. But even with the example, you'll see a question like that. It may be very similar to the example given, but you'll see this question. Yeah, X means the angle. Phase. Yeah. Yeah. Mathematically, it's exactly the same as W. It just physically, there's a different interpretation. But yeah, right. Yes, right. Yes, the physical interpretation is here X is the phasor. Mathematically, it's the same thing. It's not different. Yeah. Any other questions? I guess there's a lot of questions about homework. So any feedback on how the question should be done better? Do you guys want to see more examples in the homework? So the problem with more examples is the question will be harder. right? So I mean, I cannot give you an example and say, oh, change the numbers and do it again. That's not very meaningful. Yeah. Yes. Okay. Okay. So I can give you an example like that, but then the nonlinear regression will get harder, right? I cannot say, this is x squared. Do the next one with x cubed. That's not a meaningful expression. Okay. Okay. I'll try to do that. I want to avoid the question being very simple where you just change one line in the example. And then that will solve the problem. Right. So that's what I'm trying to avoid. So I think let's do the following. For some questions, it will be easier. Right. So it will be questions where you look at the example, you change one line of a code or you change something that will solve the problem. But I think there'll always be at least one question where you need to think a bit about the question. It's not going to be a trivial extension of the examples shown in the homework. So does that make sense? So you think the homework being, let's say, 4 questions. Let's say 2 of them will be, very similar to the example providing the homework. Maybe you construct a different H. Or I can ask you, okay, this Z measures the power flow from line 1 to 2. Have an example that measures power flow from line 2 to 3, right? So that'd be a question like that. As you don't change that much, it will be sort of a small modification in there. Then be one question that's sort of slightly harder. You have to think a bit more. Be one question that really asks you to think what you do. Yeah. Because I want to avoid a case where the questions are either so simple that it really doesn't, you sort of pattern, you can find patterns on what to change, and that will give you the answer. I don't want that to happen. I also don't want to happen the question so generic you can Google it and copy paste. Right? So I do want some question that give you some thought, some idea for thinking about it. Yeah. Right. 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 So yeah, so I'll try to do better is I'll try to provide more examples to at least get the basic concept across. I will try to have a question that stretches the basic concept a little bit, right? Test your conceptual understanding a little bit. Right. So so I'll try to construct the homework in the following way is for half or more than half the questions, so if you understand the examples in your superficial level, you should be able to do it. Basically, you can pattern match which to change. Then some questions were really testy. Do you understand what the example is trying to say? You need to understand that, then be able to do the question, right? So I will not have a question that's outside the scope of the example I will show you, right? So I think that's the main complaint is there are some questions were outside the scope of the example. So it's not contained in the examples. So this time I'll try to make every question contain in the concept that example is going to show you, but it's not going to be just change this line from the code that will solve it, right? But at least the concept should be contained in the example, right? So I'll try to do that. Okay, so I'll try to make it clear, make it some questions were right. So this has a different level of understanding of the examples and so on. Okay. Okay. Does that sound good? Does that make sense? Yeah. Mm. Right. Yeah. Right. All right. The English. Okay. Yeah. So that is actually where I want you to think about it. So I'm not going to spell that out because that's a good thing to think about. Right? That's where actually the homework should make you do is to think about this kind of equation. So if you, right, so basically the way I'll try is I will give an example, right? I'll say, this is what happens. This matrix is invertible. Now let's look at another example where the matrix is not invertible. Let's look at what we do with it. Then you may have a homework question where the matrix is not invertible in a different way, and you have to make it invertible. You can see this kind of question. Okay? So again, you should spend some time thinking about it. It's not So changing the homework this way probably would not make you spend less time on it, but probably make it more enjoyable doing the homework, right? So that's the goal be you have a better time doing the homework, not necessarily you have a faster time doing the homework. Right? So okay, so right, so last homework I thought was fairly simple, but obviously that's not the way it turned out. So in this week's homework again, it will be the examples will showcase all the concepts you need. It will not be a concept that outside the scope of the example. That being said, there'll be some questions where you really need to understand what the example is trying to say. So then you can solve it. Okay. So let's try that with this. Yeah. Right. That's probably the hardest thing about this type of course is there's not a book I can point you to read. There's not, yeah, there's not a book that does this kind of stuff. I can point you to books that would not, like you don't want to read a book on state estimation. You won't get to even through the notations of what is going on in there without basic knowledge of power systems. And so that's why I'll make the examples better. If you have questions, the best way is to yeah, can email me and ask me like what is going on. And I think I should respond to email fairly quickly. I'm on Slack. There's I don't check Slack more frequently than I check email. So email will be better for me. I check Slack less than I check email. So we I have a I'm on Slack. I'm on Discord. I don't check. Yeah. Anybody want to set up a Discord server? You can do that. I'm happy to broadcast that information to the class. We cannot set up Discord. As a university, we don't really, Discord is not an approved method of communication with people. Yeah. Yeah. So if any of you want to set that up, go ahead. I'm happy to, if you set it up, I'm happy to broadcast Discord. Yeah. I'm happy to do that. Yeah. Yeah. My free email address. Yeah. I check email fairly often, much more often than Slack. I don't check Slack very often, right? And yeah, so yeah, email me. I'll try to make the question examples as self-contained as possible. I'll make the questions or draw from the examples and whatever happened on the slides, right? That being said, yeah, it's not going to be the easy set of homework to do. I think there's sort of given that there's many people have not seen power systems, many people have not done these things before, so yeah, I'll try to improve the examples and the relationship between the examples in the homework and the actual homework questions. Yeah, I'll try to do that. So. For Discord, yeah, set it up. I'm happy to broadcast for the rest of the class. If you guys set up Discord, I don't want to run the Discord, right? So somebody else can run Discord. Okay. Any other things for feedback or homework or suggestions? Okay, good. So let's finish at least writing down the solution here, right? So this is exactly related to linear regression, right? So we're not going to spend much time, right? So okay, so good. So this is the type of homework question that we'll have. As we did linear regression, you know the closed form formula for that. So one homework question will be, can you derive the closed form formula for this? Knowing the closed form formula for that one. Okay, so that is a question I can give you. All right, so you know the closed form formula for minimizing y minus w transpose x, right? So w, right? So you know the closed form formula for this, right? We in linear regression, we give you the closed formula for this, right? So if you know the closed form formula for this, you should be able to write down the closed form for that one, right? So that's the level of some homework question is. You're given this one, can you write down that one, right? So I believe that's a fairly simple, actually, homework question, right, to do this. There'll be other things that sort of build on this, but that's one type of homework question. Okay, so not, it won't be that I give you a formula and say, do ABC, this is the answer pops up. It'll still be trying to test your understanding there. And the big thing of this kind of class is actually, can you code? One is conceptual, the other part is can you code? Can you plot? Can you code? Can you do those things? Can you present data? Right. So it still won't be that it's spelled out what the answer should be. There'll still be question like, imagine you add more sensors. How does the error look? Or can you estimate X better? It'll be this kind of question. And you have to think about how you present this kind of idea, right? So still will not be, not everything, the examples will not cover every possible thing that can be asked. You still have to do some thinking. But the idea is that will be a lot more self-contained than before. Other suggestions, other things, others? Okay, good. Right, so yeah, so again, when you homework, you have a question. Again, we don't have it here, so again, the best thing is to ask me. Right, so you can Google around. If you don't find, the Google around is going around. The best is you don't know what the command is. You can Google around. You can Google how do you solve linear regression. We'll tell you what the command is. That's perfectly fine. If you don't understand the concept or you don't understand what the problem is trying to make you do, then the best thing is to email me and ask what you don't understand. Okay, good. All right, so let's end here today. Again, you have the homework out probably tomorrow. We'll be due next week, Thursday. So we'll have another class at least on Tuesday for you to ask questions in person if there's questions, right? Okay, all right, good. Thanks.